Good afternoon. This afternoon, we're going to go through a few short details before you have your quiz. Some of these details will inform the second mini project and help you with a few kind of tips that may help you through some of the t-tests that you're working on. The other part we'll look at is just sort of a quick prep for the questions on loops, iterations, and conditionals. Okay, so we're on class 20, and happy Halloween, everyone. Hope you're having a great day so far. Love seeing the costumes around campus today. And one note here is, looking forward, probably should begin looking at inferential thinking, particularly 14, will inform some of our upcoming work on Lab 8. We will have the quiz on iterations and loops, and the mini project will be due this evening. And those of you who finish, though I would suggest working kind of fine-tuning, adding markdown, kind of improving your plots first, but you can begin Lab 8 as you go forward. Okay, so this slide, these are available in under modules in Canvas. This slide kind of gives an overview of some of the steps we took. I demonstrated this last week with you, looking at some global warming data. Now here I misspelled global, G-L-A-B-A-L, but nevertheless, if you put that aside, we're looking at the average temperature in December as a function of year. So much like in Lab 7, you can go through and get these December temperatures over the period 1850 forward. We can apply the changes function and look at every other year, and we get 17. There are 173 years in the data set, so then we can simulate the null. And then what we come up with is the following figure for the December temperature changes, and we can see the green dot reflects where the test statistic is. And then we can do the NP count non-zero of the sample generated by the iteration through the sim null. And we look for those greater than 17. That was our test statistic. Divide by the length of the sample and we get 0.08. So here at the 5% level, we cannot reject the null hypothesis. If we went to the 10% level or 0.1, we could. Okay, now let's look at this more specifically with regard to the mini project. So here, one thing is we are going to look and apply the changes function, albeit over a much narrower range of years. Previous data was from 1850 forward. In the case of this particular plot that we're examining, this is the Plains of Abraham. We're going from 1995 through 2009. Now, the original data, we have many replicate plots for each year. The number of those replicate plots is very important as you go forward, because in the t-tests, we need to be ensured that we have the same number of replica plots in the first year and the last year that we consider. So there are adjustments required there if that's not the case, because otherwise we cannot do the paired t-test. Okay, and that part I'll show you in some demonstration. So nevertheless, we have to group, okay? So here you see the grouping by the NP mean, and then it gives us the cover percent space MEAN, meaning the mean of the cover percent. You see we would get one data point per year. This is appropriate for applying the changes function, because otherwise the changes function would be looking for changes within the replicate plots in a given year. And that would have nothing to do with the changes going on as a function of time following the eruption. So I just wanted to kind of review this piece. Okay, here is a slide which kind of gives you a sense of this. Again, as I'll show you in the demonstration with the real Jupyter Notebook, A key thing is here we can see that for year 2, we have 20 data points, and for year 1, we have 20 data points. Here I have adjusted this starting year to 1989 as opposed to the statement that is here so that we will get the same number of data points on each. And then here you can see the cover percent. We get values at each for the second year for each of the replicate plots for that year. Other thing that's important is the NP mean, the parentheses are here such that we don't take the difference of mean here, we take the mean of the difference. So there's a big difference there. This occurs because these data are paired. So when we take these two arrays, such as this one, each data point for the subplot is going to be subtracted, and then we're going to subtract all of these, form a new array, and then we're going to take the mean of that new array. So that's what this difference of means is doing. And that's what we should do for a paired t-test. Okay, in question 5, we're looking at the relative growth. Again, this issue of having the same number of data points on both sides is also important. So here we can look and we see the values, but here, this is the ratio. See, ratio when we divide, that's what we have here. And then we get numbers such as this for that ratio, okay? So now what we're looking at, this is growth 2. There would be another one. This is examining my plot 2. If we looked at my plot 1, whichever one you have selected, then it would have a different ratio. So this ratio here is larger if that particular plot has experienced more growth since the eruption. So our hypothesis here is related to how much growth have we seen, and which of the two plots is likely to experience more growth. So that may be hard to assess, but use the clues that are available in the plot data from question 1 and 2 to give you a sense. For instance, if you had a plot that was at very high elevation, then you might expect that it may take longer for the recovery or for the coverage to come back in that particular plot. Or if the outcome from the eruption was particularly severe, then that plot also may experience that. Other plots may have milder effects and may recover more quickly. So that's what you're looking at in question 5. It's quite different, but the consideration is very similar in terms of having the same number, because this ratio would not work out if you had different numbers, because when you divide two arrays, you have to have the same number of data points there. Okay, we're going to look at question 4 here, and there can be some confusing points, and I want to clarify. So for instance here, we're looking at the TORD, Tuttle Ridge plot, and here we can see the years included in this plot. One thing to note is these are the replicate plots, and the number of those replicate plots at the early year and the end year will need to be the same in order to do a paired t-test, because these are the years that will start at the early time and show up in the later time. So here the length of this year 2 and the length of the year 1 should be the same. Now here min and max is put here to be convenient. However, if you find that these conditions do not match, then you can look in your data to find years that match up better. Then here we can take the diff of the means. The key thing is we need to take the mean of the difference, not the difference between the means, okay? Because this is where we're working with the paired situation. So then when we come down to examining our degrees of freedom, it's going to be the number of rows in the data set. So I've called mine data 1, which relates to the TORD plot. And here I take away 2 because of the 2 degrees of freedom used up in the mean and in the standard deviation. Standard deviation, again, is the standard deviation of the difference. So again, to get these differences here, we have to have the same number of subplots or replicate plots in the first year as in the last. And then the n will be the number of rows of data. Again, we have to constrain it to one of these years. And then this paired standard error is particularly straightforward. It's the standard deviation divided by the square root of n. And then we can go down, get things to print out, and then here we can see what the t-value is. Thank you. Okay, last bit here, and this is informative for the quiz. Here we're looking at a function. This is one of many, many ways to develop this. But here we're trying to come up with the null, basically to simulate the null, okay? So here I've made this very compact. The argument of this null sum is chances, and here I've given a default value of 173, okay? So that's when I say chances equals 173, it means by default it will be 173 opportunities. Now that default is a little large for the number of years of data we have in the mini project. More typically, we might have 10 to at most a little less than 30 years. So that would be the number of chances for this to change within the mini project. But here this is very compact because I have one, negative one. This is increase, decrease in number of chances. So this will create an array with this number of opportunities to be plus or minus one. And then if we do the sum of this, we will add in a positive way all those cases where the array came out 1, and subtract those ones where the array came out negative. And thus, this will simulate a randomly determined number of changes over those 173 exposures to change. Now, if we put in a different value here, such as 10, then it will only be 10 times. So if you had 10 years of data, this would be the appropriate thing. And here we come out with 2. Of course, here with the 10, the maximum number of changes that we could get is 10, or an increase of 10. In other words, if everything came out 1. So this is the function that can define this simulation, a single simulation. Okay, now that we have that here, I can say this is 20 times, because if we're examining a particular plot, maybe we have 20 times of data, 20 years of data that we're examining. Here I initialize the sample as an empty array, or list actually, sorry. And I'm going to do this 15,000 times. This number is critical because that has to do with the particular number of years of exposure to change that we have. The 15,000, as we increase this number, it gives us the opportunity to smooth out our distribution. So a larger number will make a smoother distribution. Although in viewing the figure, it doesn't necessarily look that way. But that's a matter of the bins that I have chosen, or the default that are given. Then this part is the iteration. So we see a colon and an indent. Now this is not a function. This is simply a loop here, or iteration. I takes on all 15,000 of these values, but we don't use I in the iteration. We simply append to this empty list each of the outcomes of the simulation. And then the last line here is outdented, and this is simply converting the list to an array. Then we can see what the array looks like, okay? And then we can plot this. We see this. And then in principle, if we knew what our test statistic was from the experimental data, we could make a comparison and get the p-value. Okay, so those are going to be key points with regard to the quiz. Okay, last part, and this is a little bit of a Halloween special here. So here I've nicely chosen randomly between 3 possible colors for a pumpkin. Most typical, of course, is orange, but we have a couple other colors. So this will randomly choose one of these colors from this list. And now the important point we're looking at is the conditional. So what happens here is this if will check if the pumpkin color is orange. If it is, this colon indicates we'll go here, and it will print traditional choice. Then we go to the elif, which we could think of as else if, but it's always spelled elif. So this will do an additional test if the first test fails. In other words, if the pumpkin color is not orange, it will go here and check if it's green. If it is green, just for fun, we'll say pick too early. Then, not passing either of these tests, it will go to this third statement. This one would be elif white. Here it says interesting choice. And then here we have an else. Note the else doesn't have a condition here. Why does it not? Because else is the backup. It's the remaining choice if nothing else of the other three statements were all false, meaning the equalities here with the double equal were not equivalent. So here, did you pick a color? Well, of course, the way this is constructed, we will actually never get to this statement. But you can imagine if someone put in a value themselves, then it could come out this way. So in this particular case, in this particular one, we got picked too early. Why? Because here the color evidently came out green. And just for fun, we said pick too early. So that's a summary of what we'd like to have in hand for the quiz. So good luck with that. And after the quiz, you can work quietly on the second mini project, and the course assistant or course assistants will be available to give you some tips. Otherwise, if you care to, you can leave and go from that point. But if you stay in the room, it's a little easier to get help from your table mates and the course assistants. So good luck on the quiz. Have a great Halloween. Sorry I'm unable to be there today. I had some travel and the timing was such I couldn't make it for the 3:30 or 5:30. And we don't have anyone to back up. But I think this video works well. Good luck again and have a great day.